Okay, I'm going to attempt to give a lecture on the Michaelis-Menten equation. Now, first we're going to talk about how to derive the equation. And basically, I'm going to talk about how to derive the Michaelis-Menten equation, which helps describe the kinetics of enzymes as they react with substrates. So to begin with, we're going to talk about an enzyme reacting with a substrate, which is right here, the first one here. And we can see that ES joins to make we can, ugh. Okay, I'm going to give a lecture on how to derive the Michaelis-Menten equation, which is used to help describe the kinetics of enzymes as they react with substrates. So to begin with, I'm going to talk about step one here, where an enzyme plus a substrate combines to make ES, or an enzyme substrate complex, or otherwise known as the Michaelis complex. If you'll notice in this reaction, there are double arrows because the reaction can proceed forward or backward. Moving on to step two, the enzyme substrate breaks apart, which leaves an enzyme and a product. And if you'll note here, it's only a single arrow. It goes only in one direction because there's not enough product is formed to make it reversible at this early stage in the process. So next I'd like to assign some variables. K1 is the forward reaction, so it would go up here for step one. K-1 is the backward reaction of step one. And K2 is the forward reaction from step two. All right. So we want to check for validation of a reaction, say. So we want to add the equations together, and when we add these two equations together, the enzymes cancel out, and it leaves just the substrate and the product. To make a steady state approximation, meaning the creation of an enzyme substrate that's equal to the sum of all reactions decreasing its reaction, reaction K1, which creates ES, minus K-1, which consumes ES, minus K2, which also consumes, which gives you a net value of 0. This instantaneous rate of change gives you this product right here. And these expressions mirror the method for initial rates, where reaction rates only depend on concentration of reactions, right down here. So the problem with this equation is that it's difficult to determine the value of unbounded enzyme. So to do that, we solve for enzyme, we solve here, and ET, which represents the total concentration of the enzyme, plus the enzyme and then the enzyme substrate. ET must equal the concentration of E, the unbounded enzyme, plus the concentration of ES, the bounded enzyme. And so we get this equation here. If we subtract ES from both sides, we can just solve for E, which gives us this. So now we can substitute ET, or E total, minus the ES, and this gives us this equation. Let's see. So now we have this equation here, which is K1 minus times ET minus ES times S minus K1 minus 1 times ES minus K2 times ES. After you distribute the K and the S, you're left with this equation down here. And the goal of this is to solve for the concentration of ES. So we want to move all the terms of ES so that they're by themselves. So we have this right here. And then we move down, when you divide by ES by itself, we get this equation here. And then we multiply the numerator and the denominator by 1 over K1 over 1 over K minus 1, and we get this. So, like I said, we already have an equation for ES. Oh, wait. So if we take ES from above, we give a lecture on how to derive the Michaelis-Menten equation. And this equation is used to help describe the kinetics of enzymes as they react with substrates. So we're going to begin with an enzyme reacting with a substrate here. And then we see the arrows going back and forth, and E plus S joins to make what's known as an enzyme substrate complex, or the Michaelis complex. And if you'll notice the double arrows, as I said, it's because the reaction can go forward and backward. Now for step 2, we have the enzyme substrate breaking apart to form an enzyme and a product. If you notice, there's only a single arrow because it only goes in one direction, because right now there's not enough product to be formed to make it reversible at this early stage. So I'd like to assign some constants to this equation, and K1 is the forward reaction for step 1, K negative 1 is the backward reaction, and K2 is the forward reaction of the second step here. Now, you want to check the validation of the reaction, so we're going to add these two equations together. And when you add them together, the enzymes cancel out, and you're just left with the substrate forming the product. Now here you can make a steady state approximation, meaning creation of an enzyme substrate is equal to the sum of all reactions decreasing its concentration. So reaction K1, which creates ES, minus K minus 1, which also consumes ES, minus K2, which also consumes ES, gives a net reaction of 0. And these reactions, for example, K1, which is, consumes the E and the S, they mirror a method for initial rates where reaction rates only depend on concentration of reactions. Now, there is some difficulty with this equation, and the difficulty is it's difficult to determine the value of unbounded enzyme E, so you have to solve for E. And ET represents the total concentration of enzyme, and ET must then equal the concentration of E, the unbounded enzyme, plus the concentration of ES, the bounded enzyme. So we subtract ES from both sides, and we solve for E. So now we substitute ET minus ES to get our previous equation for E, which is here. Okay, so now we get this equation, which is K1 times ET minus ES times the substrate minus K negative 1 times ES minus K2 times ES. So after we distribute the K1 through it, we get an equation that looks something like this. And the goal of this is for the concentration of ES. So we move all the terms with ES to one side of the equation, okay? And then divide by ES by itself, and you get this equation right here. Now, then we multiply the numerator and the denominator by 1 over K1 divided by 1 over K negative 1, and we're able to get this equation. Now, the instantaneous rate of change for a product P is a function of the reactants, and now there's only one reaction for K2, which is ES. And the wonderful part about this is that we already have an equation for ES, so you're able to solve that. So moving along, we're going to talk about velocity, or the reaction rate of an equation, and that's down here. And we have a reaction constant called Kcat, which is just another, it's also known as K2. And this is where the maximum number of molecules of a substrate S so that an enzyme can convert the product per catalytic site per unit of time, which is a fancy way just of saying the number of molecules an enzyme can convert per second. Kcat is also known as the turnover number. Now, let's see here. Now, Kcat with times the total enzyme is the total concentration of the enzyme X, maximum number of molecules an enzyme can catalyze per second if all the enzyme is reacting with the maximum number of molecules per second. Then we have the maximum rate of the reaction, otherwise known as the Vmax. Now, and here's the equation for that. I'm going to talk about what some of these terms mean in just a second. But for this reaction too, we can see that as we know that as ES increases, the rate of the reaction also increases. So therefore, we can say that ES equals E total, which means all of the enzyme is bounded or saturated with some substrate, then the reaction rate or the velocity is at its maximum. So that's how we can come up with this right here, that Kcat is equal to the Vmax. Now, let's just talk about Km for a moment. Km is known as the Michaelis constant, and it's the concentration of substrate S at which reacting rate is equal to half of the Vmax. Km is also known because it talks about affinity of an enzyme for its substrate. So, for example, if the Km is low, then a small amount of substrate is needed to reach half the maximum velocity, and that usually means that the enzyme has a high affinity for its substrate. Whereas if Km is high, the enzyme has a low affinity for the substrate. And that's basically the end of my lecture. Thank you.